Hello professors, nice meeting all of you here. Our group is Group 2 from Topic 7, and I'm Wang Qilok.
I'm Shi Yuanjing, you can call me Rachel.
And I'm Zhu Yidi.
I'm Xu Anhuoning.
So in the following presentation, we have divided the contents into three major sections. The first section is the properties and behaviors of the two materials, which is concrete and timber. And moving on to the second section is the issues and implications in terms of the short-term and long-term environmental performances. And last but not least, we move on to the final section. We will provide the coverage of professional practices with respect to use, tests, and quality assurance of these two materials. So let's get started. Okay, now let's talk about the microstructure of concrete first. Concrete is a composite material whose microstructure contains random features over a wide range of length scales, from nanometers to millimeters, with each length scale presenting a new random composite. In its actual uses, at the length scale of meters, concrete is usually considered to be a uniform material with bulk properties like compressive strength, creep, and others. This is the usual engineering length scales. And concrete is mainly composed of water, aggregate, and cement. So in this figure, it shows four microscopic views of concrete, displaying the length scales of the material itself. From the upper left is concrete, the upper right is mortar, and the lower left is cement paste, and the lower right is calcium silicate hydrate, usually known as CSH. So now let's take a close-up of the four pictures mentioned above. In the upper left of the figure, there's an optical micrograph of concrete. The bars at the bottom of this image are millimeter bars. At this length scale, the concrete can be considered to be a multi-large aggregate random composite, where the large aggregates range from 3 to 30 millimeters. So now move on to the right picture. The top right image shows a magnified optical micrograph of a piece of the matrix face from the previous image, where now the mortar is itself seen to be a cement paste sand composite. The bars at the bottom of the image are again millimeters. The size of the aggregates in this image range from a millimeter or so down to a few tenths of a millimeter. Looking closely at the matrix of the mortar composite, you can see some dark specks of the order of tens of micrometers. Actually, these are pieces of unhydrated cement. Now we move on to the lower left image in the previous four figures. It is a backscatter electron scanning electron micrograph of the cement paste matrix. From the picture, you can see here, there are some large white clumps. Actually, these are the largest of the unreacted cement grains, and this large and the largest grains in the image is around 50 to 80 micrometers. And we can also see some small dark specks in the previous mortar image here. The contrast in a backscattered electron scanning electron micrograph is provided by average atomic numbers. And so the unreacted cement grains are now the brightest phase. Cement paste is clearly a random composite material made of unreacted cement, capillary pores, and various other chemical phases that are a result of the hydration reactions between water and cement. The main reaction product phase is an amorphous or at best poorly crystalline calcium silicate hydrates jet, produced via a hydration reaction and denoted CSH in Siemens chemistry notation. And this is really the glue that holds the cement phase together. Just as the cement phase is the glue that holds mortar and concrete together. In this image, this is the gray that lines the cement grains and is clumped in between, showing where small cement grains used to be before being consumed by the hydration reaction. The randomness in the cement phase microstructure is on the order of micrometers because the original cement grains have an average diameter of approximately 10 to 20 micrometers, and these set the scale for the microstructure. Finally, the lower right image in the previous figures is a transmission electron micrograph of CSH, which is itself seen to be a complex material with a random porous nanostructure. The size of the image is about 300 nanometers on the side. This random nanostructure can also be detected by neutron scattering. So, to the small conclusion of the microstructure of concrete, the range of the random microstructure of concrete from nanometers like the CSH to micrometers like the cement paste to millimeters like the mortar and concrete to meters like the final end use covers 9 orders of magnitude in size. It is then a large and difficult task to try to theoretically relate the microstructure and the properties of concrete. And this has led to the use of computer simulations coupled with modern experimental probes, which have provided some insights into the microstructure. So, after deliberating the microstructure of concrete, now we move on to another material, timber. In this picture, we can see the microstructure of timber in both hardwood and softwood. The essential difference between hardwood and softwood is the presence of vessels in hardwoods. These are continuous pipes running the length of the tree and serve as conduits for water and nutrients in the outer layers of wood in a growing tree. The actual cells in the softwood species have the same function as the vessels in hardwoods. So the diagram shows a number of important features of wood. The cells constitute fibers and have the main direction of orientation in the longitudinal direction, which is parallel to the trunk of the tree. The individual cells are stuck together rather weakly, but parcels of longitudinal cells are bound together with a few cells that run transverse to the longitudinal axis of the wood. These are called rays. So in this slide, you can see the microstructure of a softwood. So there the main trace of the microstructure of the softwood is that the length of a longitudinal trusses is about 3 to 5 millimeters, and its diameter is about 20 to 80 micrometer. So in this picture, we can see the microstructure of hardwood, and the length of these fibers are about 2.7 to 3 millimeters, and average diameter is about 20 micrometer. So timbers are mainly composed of cells. Cells are composed of 3 main chemicals: cellulose, lignin, and hemicellulose. For cellulose is a long chain polymer with the chains principally aligned with the long axis of the cell. In some parts of the cell walls, the cellulose is spirally wound. And for lightning, the glass-like substance that serves as the filter, like the resin in fiberglass, and is brown color. And for the hemicellulose, it's a cellulose type molecule, but it's not as long as the main cellulose. It's a more mat-like molecule that is used to wrap up the cell. So we should note that the lignin, which is like a gel that will act as a bonding agent which glues the cells together. Now we move on to the crystal structure of the cellulose. Many of the important properties of timber are related to the crystalline nature of much of the cellulose in wood. 2 unit cells of the crystal structure of cellulose are shown at the right of the picture. Notice that the flat molecules fit together in a regular fashion in their long chain direction parallel to each other. This is typical of other man-made polymers such as the polyethylenes or polypropylenes. So now we do a comparison between these two materials, concrete and timber. First of all, their components are very different. The concrete is mainly composed of water, aggregates, and cements. However, on the other hand, timber is mainly composed of water and salts. Both the concrete and timber is hygroscopic. And when it comes to the random microstructure, on one hand, concrete contains random microstructure because the randomness in the cement-based microstructure is on the order of micrometers because the original cement grades have an average diameter of approximately 10 to 20 micrometers, and this set the scale for the microstructure of concrete. And on the other hand, timber is not random when it comes to its microstructure because of the crystalline structure of the cellulose. And in timber, the flat molecules fit together in a regular fashion in their long chain direction parallel to each other. So to the last fashion, the bonding agents are very different as well. In concrete, the bonding agent is the calcium silicate hydrate gel, while on the other hand, in timber, the bonding agent is the lignin. Thank you.
So thanks, Kano. I'm Richard. I will talk about thermal properties and behaviors for both of the materials, timber and concrete. And here is the content for my presentation. First, I will talk about thermal properties for both of the materials, which includes the specific heat, the thermal conductivity, the thermal diffusivity, and thermal expansion. After this, we will talk about the thermal behaviors of both of the materials. And last, we will talk about the comparison between these two the behaviors of these two materials. So first, we will talk about the thermal properties for concrete and timber. So let us start with talking about the specific heat for these materials. The specific heat represents the heat capacity for both of the materials, which means that the materials can absorb some heat from outside world. And for concrete, the coefficient is between 840 to 1170 joule per kg per Celsius degree. And it will be affected by the moisture content, by the temperature, and also by the density of the concrete. Next, for timber, the coefficient is between 400 to 840 steam units, and it will be affected by the moisture content, by the temperature, and it's one special thing. The oven dried would have a different coefficient between the green. So next, we will talk about the thermal conductivity. Thermal conductivity means that the ability for the materials to conduct heat. So for a saturated concrete, the typical value for the coefficient is 1.4 to 3.6. The saturated concrete means that the degree of saturation of concrete is a major factor for this coefficient, and also the composition, the temperature, and the density. And next is the typical value for the conductivity of ordinary wood, which is between 0.25 to 0.34, which is much lower than the concrete and is much lower than some ordinary materials. It depending on the direction of heat flow, which means that the different direction from the heat flow will cause a different coefficient, and also the moisture content, the temperature, and density. And in this two table, we show some simple concrete and also some simple timber for both of the coefficients. So the third thermal properties we will talk about is the thermal diffusivity, which means that the different parts in a mass will always have the tendency to be a same temperature, and the diffusivity means the rate for this process. And we can see the diffusivity is simply related to the conductivity. And in this equation, we can see the correlation. And the range for typical value of diffusivity of ordinary concrete is between 0.002 to 0.006 m²2 per hour. And it will be affected by the type of aggregate used, the moisture content, the original water content, which is a little special to the previous, and also the exposure of drying. And as for the diffusivity of ordinary wood, the typical value is always between 0.000423 to 0.000631 m²2 per hour, which is much lower than concrete as well. And also it is depending on the type of the wood, the moisture content, the density, temperature, and heat flow. So last, we will talk about the coefficient of thermal expansion. What does it mean by thermal expansion? It means that the mass, the substance, or the materials will always have the tendency to expand when the temperature increases. And also we can see for concrete, the value is between 11 multiplied 10 carry minus 6 and 20 multiplied 10 carry negative 6 per Celsius degree, m per Celsius degree. And it will be affected by the composition of the mass and also the state at the time of temperature change. And we can see as for timber is a little different. It's because that the different direction of the heat flow will affect the thermal expansion. And for the rift grain, it has a different thermal expansion, 2.98 to 4.28 multiply 10 carry negative 6. And as for the radius, it is between 21.8 to 30.7 multiply 10 carry negative 6. And as for last, the chart wise, it is between 29.7 to 42.7 multiply 10 carry negative 6. So it will be affected by the moisture content and the temperature. And in this figure, we can see the correlation between temperature and thermal expansion. And we can see the concrete will always have a steeper curve than the timber. It means that in the same change in temperature, it will have the coefficient for concrete will be more sensitive. And now that's the end of the thermal properties for concrete and timber. Next, we will talk about the thermal behaviors for both of the materials. So next, we will talk about the thermal behaviors of concrete and timber. First, we will talk about timber. For the thermal behaviors of timber, we will focus on 4 parts, which including the color change, the modulus of elasticity, the modulus of rupture, and the crystallinity. So first, as for the color change, we can see in this feature, the color darkens as the temperature in the process is increased. And the indicators for this process will be the temperature, the degree of crystallinity, the degree of polymerization, and the OH content. And as for the modulus of elasticity, it has a different curve when compared to a modulus of rupture. And we can see it will increase essentially at a lower temperature, which is 115 degrees Celsius degree and 135 Celsius degree. But the increase is essential, which means that the decrease will appear after the increase. And we can see it will decrease with the increase in temperature, the increase in duration of this process. And next we will talk about the modulus of rupture. The modulus of rupture is a bit different from the modulus of elasticity, which means that there will be no increase through the whole process, even from the low temperature to high temperature. And we can see in this picture, the decrease in both dry and wet conditions. And we can see in this curve, even the low temperature and high temperature will always decrease. And next it will be the crystallinity of the timber. You can see in this picture, the crystallinity of the timber will have the change curve something like that. And the dry condition and the wet condition will have a different results. And it is determined by the increase in relative rise of crystal. And next we will talk about thermal behaviors of concrete. The thermal behavior of concrete will only focus on 2 parts, the strength and the modulus of elasticity. First we will talk about strength. The strength for the concrete is quite important for the building, for it as a building materials. So you can see the first figure shows that the decrease in strength in a normal concrete, in a normal high temperature. And we can see it will be a decrease from 0 Celsius degree to 600 Celsius degree. But as for high temperature and low temperature comparison, we can see when at a very high temperature, you can see from 0 Celsius degree to 100 Celsius degree, there will be a whole tendency of decrease for strength of the concrete. But as for this chart, we can see at a negative temperature, there will be an increase in essential, which is a bit similar to the modulus of elasticity of the timber. But we can see it will be an increase essentially, but always with a decrease. And when the temperature is between negative 100 to 0 Celsius degree. And next is the modulus of elasticity. And in this part, we will talk about what is different from the modulus of elasticity of concrete than that of timber. You can see in this picture shows the tendency for the MOE of the concrete. And we can see it is the modulus of elasticity at high temperature, and it will always decrease with the increase in temperature. But the indicators for the both processes is different. It will be strongly affected by the temperature and also the aggregate used for this concrete. And you can see the variation of strength and of modulus with temperature is of the same form, which means that they have the same tendency and have. So next we will talk about the comparison of the both materials. And we choose 4 factors for this part. You can see the first factor is strength, which means that the strength for concrete is different situation in high and low temperature. You can see the strength in a high temperature they will also decrease, but for the low temperature there will be an increase essentially but decrease. And for strength of timber, it is depending on different conditions, which means that different conditions may have different results. And for the modulus of elasticity, you can see for the concrete, it will be a raise first and for a decrease. But for the timber, they will always decrease. And next, we'll talk about thermal conductivity. Why we talk about thermal conductivity? Because of the typical value for timber. For this part, is quite lower than concrete, always quite lower than some ordinary materials. So we can see that it will be used for cold storage and installation. And for the concrete, we can see the different value for this coefficient will use for different purpose. And also, when we talk about the mass loss, you can say the concrete, because of the concrete, it is a concrete. The mass will not change for the hardened concrete. But for the timber, the higher the temperature, the less the mass loss. So that's the end of my presentation. Now let me pass my time to Andy to talk about the AAR and ASR.
Thank you, Richard. Next, I will talk about the environmental performance of concrete with focus on alkali aggregate reaction and alkali silica reaction. Alkali aggregate reaction is a reaction between alkaline content and reactive minerals in aggregate in concrete when moisture content is present. And AAR will negatively influence the performance of concrete. And this is the parts to be covered. First, the types of AAR, and second, the causes with respect to the reaction principle, sources of alkalis and reactive minerals in aggregate. And third, the implications regarding the concrete quality and economic effects, and some examples will be given. And last, the method of avoiding and controlling AAR will be talked about. And there are three types of AAR: alkali silica reaction and alkali silicate reaction and alkali carbonate reaction. Alkali silica reaction is a reaction between alkali and amorphous silica in aggregate, which is hygroscopic and will produce alkali silica gel. And the chemical equation is shown here. Alkali silicate reaction is similar with alkali silica reaction, but the reactants are changed to alkali and silicate in aggregate. And alkali carbonate reaction is a reaction between alkalis and clay in the lomatic limestones. And according to the report of the Development Bureau in Hong Kong, the majority of structures affected by AAR is found due to alkali silica reaction. And alkali silica reaction is the only type of AAR occurs in Hong Kong. And here are the steps of ASR. First, the reactive minerals within the aggregate particles contact with alkali hydroxide, and it progressively transforms into a alkali silica gel. And then water and various ions in pore fluid flow into the gel, and the gel spreads into the cement paste. And finally, the cracks occurs when local pressure generated by expansive reaction at local sites exceeds the tensile stress of the aggregate particles and cement paste, as shown by the third picture. And there are some microscopic views of ASR. This picture shows the expansion force induced by alkali silica reactive siliceous limestone particles, which causes cracking of the particle and surrounding cement paste. And this is a thin section showing ASR damage. And this picture shows a flint sand particle embedded in cement paste. The flint particle reacted expanded and cracked, and the cracked extends out into the cement paste. And here are the necessary conditions of the ASR concluded from the principle. First, high concentration of alkali hydroxide in pore fluid is needed. And second, there should be aggregate with reactive minerals. And finally, sufficient moisture content should be present to both sustain the chemical reaction and for the expansion of the gel. But it should be pointed out that there are wide variations in the above conditions because of concrete elements affected by ASR respond quite differently from one and another. And here are the sources of alkalis. Cement is the main contributor of alkalis in concrete. And also, alkali may be released by alkali-containing minerals in aggregate. And third, chemical admixtures. Some of the chemicals will contain sodium and potassium compounds. And water may also contain alkali because of ionization equilibrium. And finally, there may be external sources of alkali. For example, soils and de-icing salts may increase the alkali content on the surface of concrete. And as for the implications of AR, it is mainly focused on concrete quality and economic effects. For concrete quality, it will reduce the concrete strength and concrete durability. It will also affect the structural appearance. And in Hong Kong, ASR damage need around 10 years or more to become vulnerable. And regarding economic effects, it will shorten structural service life and increase maintenance costs. And here are some examples of ASR damage. The pictures on the top are the picture taken from Shek Wu Hui treatment plant in Hong Kong. And we can clearly see the map cracking of the concrete. And the pictures on the bottom are the condition of ASR of Daqing Railway Bridge in mainland China. And the method of control AR in Hong Kong is mainly focused on the necessary conditions. And for the reactive minerals in aggregate, we can control it by precluding the use of reactive aggregates and using cementitious replacement minerals. And for supply of moisture, we can reduce the excess of moisture and maintain the concrete in a sufficiently dry state. And at last, the total alkali content of the concrete should be compliant with the specifications of PNAP 180. The reactive alkali of concrete expressed as the equivalent sodium oxide per cubic meter of concrete shall not exceed 3.0 kg. And the calculation method of equivalent sodium oxide content is shown here according to PNAP 180. And the calculation should be prepared by authorized person or registered structural engineer and submitted to the building department. And next, I will talk about the environmental performance of timber. Under proper condition, timber has excellent and long-lasting performance, but its performance will be influenced by some elements. First, the fungal activity. Fungal activity will cause decay and corrosion of timber. And second, insects such as termites will cause void in timber and damage the load-bearing ponds. And finally, it will cause collapse of structures. Termites has excellent reproductive ability, so that it should be strictly controlled. And here are the methods to protect timber. We can control the moisture content inside timber to prevent the establishment of decay fungi. And the moisture content inside timber expressed by the ratio of weight of water to weight of dry timber should be kept under 19%. And we can use decay-resistant species of woods to prevent the decay and corrosion. And second, as for termite and second control, we can first grade the building away from the foundation. As second, if possible, cover any exposed ground with polyethylene. As third, ventilate cross spaces whenever applicable. And finally, we can use preservative-treated wood to improve the service life under severe conditions of timber without altering its basic characteristics. And finally, we can conclude the environmental performance of timber and concrete and compare them in this table. For short-term implications, the ASR in concrete will reduce the stress of concrete in 2 years, but timber will collapse in 1 to 2 years without control. And for long-term implications, ASR will affect the appearance of concrete and will require maintenance or demolishment of the concrete to guarantee the safety of the structure. And for timber, it calls for maintenance and pest control, which will cost a lot of money. And for protection methods, we can control ASR in concrete by controlling the necessary conditions. And for timber, we can control the moisture content inside it and prevent it from contacting with ground and use preservative-treated wood. Finally, let me pass the time to Michael to talk about the professional practice of them.
Thanks, Andy. And now I will give some basic introduction of the professional practice of concrete and timber. The professional practice includes 3 aspects: the use, test, and quality assurance. The first part to be introduced is the use of concrete and timber. This slide provides some general steps for making concrete. These steps come from the course materials of BRE261 Industrial Training Center. The first step is calculation, and to calculate the amount, the diameter, and the demonstration of your concrete, and the formwork mating. This step will use the timber and wood-based materials and amount oil applying in order to set out your formwork on the finished step. And material benching is mean to measure how much materials you will use in this step. And mixing and slump testing. Actually, slump testing is a producting test for measuring the quality of concrete. And then it's cube making and concreting and compacting and finishing. Actually, at this step, the concrete is already made. But in order to ensure and estimate the quality and the suitability of the materials to be used in a construction site, several tests should be carried. And these 4 steps is mainly for checking the quality and suitability of the concrete we have made. In the construction process, various timbers and wood-based materials are used in kinds of aspects, and those aspects is shown in these two charts. The first one is timber types. There are many types here, and there are oak, larch, Sitka spruce, Douglas fir, Scots pine, western red cedar, ash beech, and etc. And for uses, it is widely used in the construction site for scaffolding boards, fences, tools, formworks, and marking boards, and some other indoor and outdoor facilitators. And the clarification and statistics may not be 100% accurate because different construction sites have different situation and consideration to be concerned, and different company or firms should have different standards for this clarification. And also, this information comes from online resources, and so it may not suit the situation in Hong Kong. But this chart is enough to see how the timber is used for the construction industry. like coins have two sides. Each kind of materials may be, on one hand, the most suitable and reliable materials in some construction site, but however, on the other hand, can be even the cause of reconstruction. And here list the advantages and disadvantages of the applying for concrete and timber. Again, this information may not be certainly accurate, but it is enough to see the things behind the widely application of concrete and timber. The first, you can see that there are both 7 advantages of timber and concrete. Through this advantage, we can see that timber and concrete both have big benefits for the construction industry and also have very convenient use of weights or methods to measure and to perform the construction works. And for the disadvantages, or we can call it potential problems, it is caused by the general character of the materials, because it cannot be avoided. So we will carry various tests for quality control to maintain or to avoid, to reduce these potential problems for concrete and timber. And these materials statistic is not completed because due to some reason we cannot put enough or the full materials here, but it is enough to see how it is widely used. This slide starts the second part of professional practice, the test of materials. As we have mentioned before, this test is mainly focused on the quality control and avoid of the potential problems mentioned in the previous slides. First, as for concrete, there are 2 kinds of tests. For fresh concrete, slump test, air content, unit weight, and compressive strength is common used. And for hardened concrete, visual test, microscopic test, permeability test, and movement test is very common in the construction site. For concrete, we must be sure how it can load the compressive strength and how it can work to support the load from the buildings or as beam to support the roof, such etc. And for timber, there are not such clarification because but they still have 10 tests. Again, this is a British standard, may not suit Hong Kong situation, but it's very similar. And this may not be the whole or 100% accurate, but it shows general information and we can have a basic knowledge of a test of timber. You can see that there are gravity and weight test, impact, compression, Janka indentation, shear parallel to grain, static bending, cleavage, tensile, permissible variations, radial and tangential shrinkage. These 2 kind of materials tests are very similar but also have difference, and you should take proper test for special purpose in your construction site work. Apart from the tests listed before, there is another important element for the materials test. It is called the thermal conductivity of various materials, and the definition of thermal conductivity can see from this site. The property of a material's ability to conduct heat, it appears primarily in Fourier's law for heat conduction. And the equation of the thermal conductivity is as here. And if we are going to measure the thermal conductivity of one certain materials, we can use this equation by measuring these elements. And here lists some common materials thermal conductivities. And for these values, the lower the value is, the more property of materials to conduct heat. So it means that if concrete stone is 1.7 and water is 0.6, then concrete stone have heat can transfer through concrete more easily than water. And why is thermal conductivity important? Because it shows the ability of the structure use the materials to weather or to adjust its temperature and other elements of the indoor environment. So it is very important for engineers. And for the measurement of the thermal conductivity, we have summarized some methods to measure it. These measures is summarized from BRE261 and online sources. This is all our work, and it may not be accurate, but it may have some practical purpose and application space. And you can see that there are only four steps, and each step is need very specific tools. And the limitation is that we don't have those tools and the time to measure this thermal conductivity. But it also have given us a guide to measure the elements or other elements of the materials in the future. Last but not least, the third part of the professional practice is quality assurance. Actually, this can be the most important part of the professional practice, because only you have ensure and estimate the good quality of materials can you say that you have finished the materials usage. And for the quality control methods, different materials have different methods, and within this method, you should choose proper methods to in order to measure in specific situation. And low quality will cause seriously reconstruction or bad structure, and good quality may benefit the whole structure or the whole building. And if we are going to perform any construction work in the future or in our career, the quality control or quality assurance is very important step for us.
So here let us draw a short conclusion of our presentation. First, the materials assigned for our group topic is concrete and timber. And then for our content part, we talk about the microstructure for concrete and timber, and then thermal properties and behaviors. Next is the environmental performance of concrete and timber. Last but not least, we talk about the professional practice for concrete and timber in an application used for daily life. So thanks for listening. We are Group 2, Topic 7.